So I'm going to repeat the proof from class today that I botched up that was given a recurrence that is sort of like 1 if n equals 1, and it's a 2t of n over 2, so this is a recursion sort or max subarray, plus some constant times n if n is greater than 1. So the idea is we're trying to prove an exact recurrence without theta involved. We want to prove that t of n is equal to some constant times n times the log of n plus some constant times n. We're going to use proof by substitution, which is a type of inductive proof. And we need to start by showing the basis step. The basis step is kind of proving what is t of 1. So in this case, t of 1 should be equal to a constant c. I think I wrote it down wrong. So the recurrence should be t of n equals a constant c if n equals 1, and equal to that expression when n is greater than 1. So t of 1 should be equal to, and if we look at what we're trying to prove, we need to show that it's the same as c. So c times n log n plus c times n should be equal to c in order for the basis step to be true. And n is 1, so we're looking at 1 times the log of 1. The log of 1 is 0, so that whole first term cancels out. It completely cancels itself out, and we're left with cn. And of course, n is 1. We're looking at t of 1. That c is gone too. So all we're left with is that 1c, which is exactly the same as the base case of our recurrence. So we've proved the basis step here. So there's the c from our recurrence. You can check that off. So now that we proved the basis step, the next step to an inductive proof is to kind of prove the recursive part. So we're going to do this inductive part, and we're going to assume that we're dealing with n as powers of 2. So we can assume that the recurrence is true for n over 2. Our recurrence here is 2 times t of n over 2. We should always start by rewriting this, plus c of n. And for the inductive proof, we look at the subproblem, and this is involving a smaller n, and we're kind of using a strong inductive hypothesis here. We're assuming it's true for all smaller n. So we can substitute our inductive hypothesis here, which is that cn log n works. Of course, here we got n over 2. So it's cn over 2 times the log of n over 2 plus c times n over 2. So we're assuming that which we were to prove is already true for a smaller problem. And now we've got to simplify that, and if we're lucky, everything will cancel out. So we can cross out the 2's, and we can cross out the 2 there. Be careful, that n over 2 is actually the argument to the logarithm. You can't cross out that 2. So when we expand this, we're given c times n times the log of n over 2. And we're adding c times n, but we already had a c times n on the outside, so we end up with a total of 2 times cn. So that's not exactly the same as what we're trying to prove, but the log of n over 2 is equal to the log of n minus the log of 2. So we have c times the log n log n minus c times n times the log of 2, just using the logarithmic identities. We kind of have, since we're dividing, the log of n over 2 is equal to the log of n minus the log of 2. We're exploiting that fact here. And of course the log of 2 is 1. So we're left here with cn log n minus cn, and then we're inheriting a plus 2cn from the previous equation. So if we look at the minus Cn and the plus 2Cn together, we end up with a total of just C times n, which is what we're trying to show. I'll write it out. We have C times n log n plus now 2 minus 1, which is just C n. And it's important that we got Cn log n plus Cn, which is exactly the same thing that we were trying to prove. Oh man, it's hard to draw a long straight line here. There we go. So we have Cn log n plus Cn. It's important that we were able to use only our inductive hypothesis and algebra to recreate exactly the thing that we were trying to prove given the inductive thing. And if you're not familiar with inductive proofs, the idea is you prove the basis case, and then you can prove an inductive part assuming it's true for the basis case. And inductive proofs allow you to kind of hopscotch through all the other possible solutions. So as long as n is a power of 2, this proof would work, and in fact this proof works in general. This is really how the substitution method works. There are a few gotchas, but I'll show them to you separately, and I'll make another video that shows how you do this when you have asymptotic notation involved.